So, good morning to everyone. My name is Elena Bassoli, and I'm glad of chairing this session this morning, which is about the vehicle architecture from a powertrain system approach. My field of expertise is additive manufacturing and manufacturing technologies in general. So I'm a bit at the side of the topics today, but there's a high interest in the connection between these technologies we are going to see this morning and the capabilities of, for example, additive manufacturing, new materials, new ways of producing parts. So I'm really curious to hear about to hear the presentations this morning, and I'm happy to leave the floor to our first speaker, who is Professor Barater from Università di Modena and Reggio Emilia. Please.
Thank you, Elena. So in this presentation, I try to summarize the result of the research and the project that we are doing at the Melting Lab, which is the Laboratory of Electrical Machine and Drives of the Enzo Ferrari Department of Engineering of UniMoRe, about the topic of wide bandgap-based power converter, in particular in the vehicle electrification. Power electronics based on wide bandgap devices is seen as one of the key technologies for electrification of mobility. And in the next few years, we need a strong technological improvement for high current, high voltage power devices and low losses, high efficiency power converters, in order also to decrease battery size, which affect the overall weight and cost of the entire vehicle, especially if we are considering the global vehicle demand forecast for the next few years. And electrification is playing a big important role not only for on-road vehicles, but also for off-highway vehicles. Here in the example here, the more electric tractors, where you can have aside the conventional traction, as well the electrical energy and power generation due to the power takeoff that we can have in the system. So power electronics in electrification of transportation means DC-DC converters that are fundamental because they provide power to the different voltage level of the system. They are usually insulated power converter and increase the switching frequency. So with new power devices, it's very important since we can decrease the size and the volume of the transformer, the high frequency transformer that we can have there. The DC-DC converter are also important when you can have different storage technologies, like in the case of long-range vehicles, where maybe you can have technologies with high specific energy, like fuel cells, for instance, combined with other technologies with high specific power, like supercap and even battery. So in this case, you need a suitable power electronics, like in the case here on this example of quadruple active bridge, where you can have power electronics, the DC-DC converter with multiple sources, and you can have a smart energy management in order to provide power and fulfill the power demand from the load, considering constant power from the fuel cells and the peak from battery and supercaps. Power electronics also mean DC-AC converters for traction drives. In this sense, the trend at the moment is to increase the rotational speed of the electrical machines, that for the same rated power can consider electrical machine with lower torque and so lower volume, and so increase power density and torque density. So this is very good for the electrical side, so it's not the same for my mechanical engineers colleagues, considering the increase of the rotational speed of the electrical machine. But in any case, we need high-speed electric drives. And there are different type of drives that we can use here. In the example, you can have a voltage source inverter, 2-level, 3-level, multi-level, and also current source inverter. So the important thing to understand here, since there are as well my student here in the floor, is that if you are considering different architecture of the converter, you can have different THD of the output voltage and current, so different quality of voltage and current supply in the electrical machine. And this means that this is going to affect the overload power losses of the electrical machine, so copper losses, core losses, and also magnet losses. So when we are considering the system, we need to consider power losses not standalone for electrical machine and for the converter, but also the effect of the converter in the total power losses of the system. And wide bandgap devices are very good for this, since they can have very fast commutations, and also they can operate efficiently at higher temperature. So this means that we can push in the integration on the electrical machine side and the battery side. We can have inverter with lower current and torque ripple, which is very good for vibration and NVH. And also we can also consider to have high bandwidth control, and also have the control of power injection in multi-harmonics for the electrical machine. So this is quite different to the approach that we have today, where electrical machine are designed in order to have the fundamental of the back EMF and very low harmonics. But if we consider high bandwidth control, we can also control power at the different harmonics. And this could be good, considering also the fact that we are going to have electrical machine without rare earth material, so without magnets. So this are the subject of this new project, SCAPE, switching cell array-based power electronics conversion for future electric drives, which is funded by the New Europe Scheme of Funding of Research, Horizon Europe. So we have said that wide bandgap devices are good for a number of reasons, but we have as well some design challenges, especially if we are considering EMI, and also if you are considering the lifetime of the insulation system of magnetics that are involved in the system. So to understand that, so just let's look at the waveform of a typical PWM voltage supply in the electrical machine. So if we analyze the spectra of this, we have that this one is related to the rise time and fall time of the waveform and the period of the waveform. So in this way, if we are considering that with wide bandgap devices, so silicon carbide, gallium nitride, we have an increase more or less of a factor of 10 for the voltage slope and also for the switching frequency. This means that we have the EMI envelope which is shifted to higher frequency. And this one is challenging for the design because we need to consider all the parasitics that we can have in the system. And we can have parasitic for inverter, where both in the differential mode and common mode pathway, we can have always some capacitive coupling. And so, considering that we have high voltage variation during too fast commutation, we can have circulating current in the system, and we need to consider that we need to avoid this current in order to be compliant with standard. And considering the increased commutation speed, this is not a trivial task. So we have the same also for the CDC converter for high frequency transformer, because we are using planar technology for this in order to increase power density, where we have interleaved solution for the primary and secondary of the transformer, which is very good in terms of reducing AC losses, but we are also increasing the interwinding capacitance. And so if we have voltage variation between primary and secondary, we can have current through this tray capacitance, and so we can have circulating current. The other challenge is related to the lifetime of insulation system of magnetics that are affected by very fast commutation due to two main reasons. The first one is the impedance mismatch that we can have in a typical system where we can have inverter, cable, and electrical machine. So we can have a difference in the impedance from the cable, electrical machine, cable, and drive. And so what we can have in the result is some voltage ringing, which is increasing the voltage that we have at the terminal of the electrical machine. In addition to that, we have that the voltage does not distribute evenly within the winding of the electrical machine, but is strongly affected by the waveform of the voltage waveform and of the rise time of the PWM voltage. So we can have that the first turns in the windings are affected more, are overstressors compared to the last one that we can have in the windings. And with the combined effect of these two reasons, so what we can have is that we can have an increased voltage stress for the face-to-face, face-to-ground, and turn-to-turn insulation in the system. And if the voltage exceeds the partial discharge inception voltage, we can have even partial discharge, which is an electrical arc, and so a disruptive event for the insulation system. So at this point, what are the parameters affecting more the insulation system of magnetics? So for understand that, we need a model, an accurate model. So we can have a model for the system. This is based from literature, from an empirical approach, where we can have that the equivalent model, the parameter of the equivalent model are tuned in order to have simulation matching the experimental results. Then we can have a more accurate model for the voltage distribution in the windings, where we can have each coil turns model as a transmission line with coupling inductances, coupling capacitances, and here on the right side you can see the cumulated voltage drop that we can have in the system, where the majority of the voltage drop is in the first turns of the windings, and this strongly depends on the rise time, and so on the commutation time of the power devices. So for doing so, we have finite element simulation with electrical field simulation for the capacitances and electromagnetic simulation for the inductances. And then we can have a complete model where we can have the system model in input to the high frequency model of the coil with the parameter coming from the finite element simulation. And we can have information of the voltage at the different nodes, which are the one with the blue arrow here in the system. So this is some experimental results to validate the model, and since the model is validated, you can use the model in order to predict the voltage stress in the different point of the system, and so design your insulation system in order to optimize the design of your electrical machine and not to over-design the insulation system of your electrical machine. So there are different possible solutions, since the phenomena is complex, that can act at the electrical machine design level, materials level, and also at the system level with passive filters, and at the inverter level with active dV by dt control, with the inverter, which are specifically designed to reduce dV by dt, and also the so-called smart gate drivers. So there is no time to speak about all these solutions, even if, some presenter is missing, but I guess there is no time. Any case, so I remind you to the project link of this European project, where you can find all the information related to the solution that we have proposed. Just to mention one related to the inverter architecture, what we have is that, in general, if we are considering to increase the number of levels of the voltage that we can have at the output of the converter, what we have is that the voltage jump at the change of state of the converter is reduced. And so also the electrical stress for the windings and also the EMI issue is reduced as well. So one of the possibilities is to increase the number of levels, but of course we are increasing the complexity and maybe the power losses of the inverter. So with this comparison, considering the conventional solutions with 2-level and 3-level converters and some innovative solution that we have proposed in this paper that are going to have the same effect, but considering higher efficiency, electrical efficiency for the converter. So these are just the results that you can see for the face-to-face, face-to-ground, and turn-to-turn voltages. And as you can see, what we have for conventional 2-level and even 3-level converter, what we have is that the voltage stress strongly depends on the rise time of the waveform, voltage waveform. So faster the commutation, higher the voltage stress that we can have, for the insulation. Instead, for the solution proposed, which is the red one here in the graph, we have that the voltage stress for face-to-face, face-to-ground, and third-to-third voltage is independent of the rise time. And so we can have a very efficient solution, minimizing the effect of fast commutation for the devices. So I guess that's all. So thank you a lot for attending.
So thank you very much, Davide. It would be, well, if there's a question and answer session at the end, but if there's any specific question now, I think we can still find a few minutes to answer. Doesn't seem so. So thank you for the moment. And then we can move on to the second presentation by Mr. Steve Roberts from RECOM Power.
So, welcome to the second speech, which is about EV charging. I'm from RECOM Power. We make low power AC-DC and DC-DC converters. And I want to show you where our products feature in EV charging. It's a big business for us, and we can help you make EV charging designs very simple with our products. There's a quote here from Volta, which is, "With great power comes great responsibility." You may more likely know it from the Spider-Man movies. But it is basically because an EV charger in a house is probably the most powerful piece of electrical equipment you have. If you have a small charger, it may be 3 kilowatts. And if you have a larger one, maybe up to 11 kilowatts with 3-phase supply in your house. And there's nothing else, no other piece of equipment in your house that has that kind of power, except maybe your oven is the closest you'll come with maybe 3 kilowatts. So it's very important that an EV charger is safe and reliable and secure for domestic use as well as for public use. Is it okay? Too quiet?
Yeah.
All right. Sorry, there's a lot of echo in this room, and I have to speak very loudly. Sorry. And as we've seen from the last slide and from many other people that were presenting here, there's a lot of work being done in EV charger design, choosing the right topology, choosing the right architecture, and choosing the optimal components. But I think the main technical challenge is not just the power stage. Because different EV charging applications require different solutions. So as I said before, the single phase AC-DC 2.3 kilowatts up to maybe 3 kilowatts is considered to be slow. What's called fast, or even sometimes super fast or rapid, is the 3-phase. You can go maybe 11 kilowatts at the bottom end up to maybe, for a public charging point, 50 kilowatts. And for a supercharger or ultra fast, you're talking about much higher powers, using much higher voltage AC-DC, or more likely DC-DC. If you're going to charge a electric car with a big battery in less than 30 minutes, you're going to need hundreds of kilowatts of power, and it's most likely to be DC. You'll bypass the onboard charger and charge the batteries directly. There's a quote here from a journalist in the UK, and he said that about 5,500 chargers in the UK are categorized as slow, which he calls awful. And 13,000 are fast, which he calls really slow. And only 3,400 are just rapid, which he calls slow. is that they're all slow, and only 900 are what they call ultra fast or ultra rapid, which he says is okay. So this is the problem. There's a big difference between what the customer expects and what the system there is at the moment. So the majority of EV users say the charging times are too long. This is a poll done last year. And so therefore we need higher power but faster charging. That's obvious. We may even have to cool the cable when it's getting to really high power. So I've seen some designs where they have water-cooled cables. Personally, I don't like the mix of water and electricity, but if that's what has to be done. And all of this means you have to have much higher safety levels. As I said before, in a domestic area, this is the most powerful piece of equipment you probably have. Outside, if you have it on a public charging point, you've got the added problem that it's outdoors, it's subject to abuse. So safety is the most important thing for charging. And the way that's done is with all of these different, most of the charging points I've seen are a Type 2 for Europe, but other countries have different designs. And these are called the EVSE, the electric vehicle supply equipment. And that has to have protection against misuse. And the way that's done is using the pilot wire, which is what's shown in red here. And this pilot wire handshakes with the car. It basically means that power is not supplied to the car unless the car is ready to receive it. Because therefore someone could trick the charger into causing an electric shock, and maybe that's just too dangerous for the people to use. So before you turn the main power on, you have to check, is everything safe? Is everything corrected properly? Is the car ready? Is the power supply ready to deliver the power? Then the power turns on. That's a very basic safety regulation that's covered by these 3 standards I've written there, the IEC standards and also the ISO standards. And therefore it makes sure that the system is safe. And this is even more problematic with the idea that people should use their cars as a battery and use it to have a smart home. Now you've got power flowing in both directions. This is causing all sorts of problems. Everyone says, oh, this is a good idea. Yes, it is a good idea. Unfortunately, it's a very difficult legal idea. What happens if something goes wrong? Who's responsible for it? If your car turns out and you get an electric shock from your oven, is the problem the car or is the problem the oven? Or is the problem your electrical distribution box in your house? Legally, it's a nightmare. So although everybody says it's a good idea, I think it will take a long time before people can use cars as batteries in their house. So therefore, I would be a bit cautious about such ideas. So bidirectional, no, but unidirectional, obviously. The other problem with home charging is that everything has to meet the standards as well. And this is the main standard you have to meet, or it's for the technical side, is what's called the overvoltage category. And that has to be overvoltage category 3, which means it has to have reinforced isolation, it has to withstand certain surges, and it has to have certain separations inside to protect the equipment. This applies to the main power supply plus any auxiliary power supplies inside. So you have to be very careful. You can't just build your own power supply and put it in a house, and you will not meet the standards. On the other hand, it's really simple. This is a home charging unit. That's all there is inside it. There's almost nothing inside there. Basically, all you have is an auxiliary power supply, which is what we provide, this little black box here. A little circuit that sends the information down the pilot wire to the car and says, are you ready to receive power? All of the intelligence is in the car. You've just bought a car with an AI driving system in there, why not use it to control the charging? And if the car says, right, I'm ready, I will control the charging, I will control the battery charging level, and then when it's ready, it just sends a signal back, turns the main contactor on, and away it goes. So when you look at this image here, you see there's very simple, there's a controller or an auxiliary power supply to provide a relay which turns on the main contactor. The other thing is this, we talked before about safety. In order to make the handshake for all cars the same, they've used an extremely simple system. It's not digital, it's analog. So you can see the red line at the bottom there. Basically it provides 12 volts. When the car is connected, it pulls it down to 9 volts. Then the the charging unit sends a PWM signal, 1 kilohertz, saying, this is how much current I can give you. Maybe I can only give you 2 kilowatts. Maybe I can give you 3. Maybe I can give you 10. Maybe I can give you 11. It just, you know how it's been programmed, connected up. And then the car says, right, okay, I can accept that much. I know how fast I can charge the battery. And away it goes. And if either side pull the signal down to 0, it stops. So you might say, well, why are wall boxes so expensive? Well, there's a lot of marketing in there, but that's basically all you need. But it is limited, obviously. That's okay for a domestic one. And the reason why it needs to be simple and cheap is that we need millions of these. If every new house in the UK that's being built from this year, if it's got a driveway, if it's got a garage, it has to have an EV charging point by law. Every big block of flats that's being built with an underground car park has to have an EV charging point by law, because the governments want EV charging points everywhere. So they're making it by law. So if you're going to make millions of these things, they have to be cheap, they have to be reliable, they have to be simple. And much simpler than that, there doesn't exist. So we make the power supply for the auxiliary side. It's not very high power, it's only a few watts, but it has to meet certain regulations. So that's what we do. We make sure that you can make a very simple power supply. We take care of the certification for the power supply, for the auxiliary power supply, so you don't have to. Public charging is a bit different thing altogether, because you need much more intelligence in the charger. It's much more liable for abuse, and also somebody has to pay for it. If it's in your house, it goes on your electricity bill. Simple. If it's a public charger, you have to pay for use. So that needs some sort of communication, it needs some sort of charging system. It probably needs an alarm system. There's a lot of vandalism that takes place. You probably need some sort of secure, cloud-based 5G cellular system, and it also needs some interface to the user itself. The EU has passed a law that says all public chargers will have to have a card reader. This is probably not a particularly good idea, because all cars have to have a SIM card inside them, so the car itself could charge the electricity cost to your account. It doesn't need anything else. As I said before, the car is very intelligent, but the EU wants to make it open to everybody, which means on every single charging point built in the next few years, it will have to have a card reader. Card readers mean secure communications, and it means a much more complex system. So my simple drawing now becomes something like this. You've still got at the top the auxiliary power supply that turns on the main relay, but you've got lots and lots of other components inside the charger. And this is why some of the chargers are several €100 or even thousands of euros, because there's a lot more intelligence inside the charger and a lot more security inside the charger. This is also good for us because we make lots of DC-DC converters as well, and you need all of those for all of the various microprocessors, displays, cloud modems, even LED lighting, so you can see what you're doing at night. So it's all good for us. And so we have a lot of products that we can use to help you build a more advanced EV SE charger. Finally, if you're going to do fast charging, as I said before, you probably have to go to DC or and have a much more complex power stage. That typically has a stage like this here, where you have the PFC at the front, then you have the standard AC/DC converter to charge the battery. This is probably the most basic design you can use, and that has 14 transistors in there, which is also good for us because we make isolated power supplies for the gate drivers. So we have lots of products that you can use to make your power stage much easier. So if you want to have an isolated power supply for your gate driver, we can also help. And we have lots of different products that will do that, whether you're using GaN or SiC or IGBTs or even silicon FETs, they're still good for many uses. So it's very briefly through it all, but the conclusion is that if you've got high power EV chargers, you need multiple low power internal power supplies to create a very fault tolerant, a safe and very reliable power infrastructure. You have to be careful, make sure that if you're going to do anything with direct connection to the mains, it meets the regulations, mainly this over voltage category 3 is really important. Use isolated DC-DCs to provide safety, and for the internal distributed power architecture. RECOM is a specialist for this kind of products. We've got over 30,000 different products in AC, DC and DC-DC. So let us help you bring your EV charger design to life. Thank you very much.
Thank you again. Should there be any question immediately? I think we can include this. Maybe one.
Thank you very much for the presentation. So very, very interesting. So considering also not only the technical aspect, but also the legal aspect. So in terms of one of the last slide that you have shown, so in terms of the DC-DC converter for gate drivers, so how the wideband devices are impacting or this type of DC-DC converter for high insulation. So in that sense, so considering that in the future we are using wideband devices, so what are the main challenges that you can have for the main challenges that you can have for this type of DC-DC converter for gate driver?
On? Yes. What? 1, 2? Yes. Hear me. Okay. Yeah. For the DC-DC for the gate drivers, there, as you mentioned before, one of the problems is how does the isolation cope with the spikes? How does it cope with continuous stress, DVDT and DIDT stresses? What we found is that very often if you isolate both the high side and the low side, not just the high side, you can solve a lot of problems with any kind of inductive mismatches in the tracks. So therefore, you need actually a lot more DC-DCs than you might think, but it makes the design a lot simpler. The DC-DC itself has to have probably a reinforced isolation when you're switching at high voltages. So maybe 5 kilovolts AC, reinforced isolation. And it also has to, we've done some long-term tests with very high stresses, so 65 kilovolts per microsecond switching. Is it better to use this one? Okay. Just to see how the isolation would withstand long-term abuse, basically. And we found no changes in the PD inception point after 1500 hours at plus 85, switching 1000 volts. at 65 kilovolts per microsecond. So we've done tests to make sure that the isolation is reliable long term. And yeah, we've got lots of applications that are using them, because one thing is to test it and show that you've done the scientific research. The second thing is, where's the market feedback? How many people are using this in a real life situation for years and saying they have no problems, there's no failures in the isolation? So the other thing obviously is that you need different output voltages. You might need asymmetric output voltages to drive the gates properly. So for a GAN you need +6 -1. For a SiC you might need +15 -3. For IGBT +15 -9. So we make a whole series of different converters with different output voltages to make the driver. I say we don't make EV chargers ourselves. Our job is to provide you with the tools so you can make your EV charger easily, simply, and meets all the regulations.
Good. So we can probably move on to the last presentation by Mr. Morelli from a Skyworks solution. Please.
Okay, good morning, everybody. Okay, yeah, okay. Okay, good morning, everybody. I'm Massimiliano Morelli. I'm the field application engineer in Skyworks. Maybe you are not familiar about the Skyworks technologies. Skyworks technology entered in this kind of market since last July due to the acquisition of one division of Silicon Labs. Silicon Laboratories was one of the manufacturers of digital isolators, any kind of gate drivers for all type of transistor, starting from the MOSFET to the GaN-FET technologies. So we are not new on this market. We are in this market since more than 15 years. We started developing industrial parts, and then we understand that the automotive application was starting growing a lot, but also it was requiring a lot of effort to provide all the documentation that the car manufacturer and tier one's customer are asking for, this kind of type of application. If you want to enter in automotive car manufacturer, you need to provide all type of quality support. So you have to provide a higher level of quality in terms of failure analysis report, in terms of documentation you have to provide to them. So we are, all our parts, also from the point of view of the industrial part, all are already qualified SEQ 100. But for a specific automotive application, those are also full automotive qualified. And we have a separate part numbering in order to offer this kind of differences. Inside a car, if we speak about hybrid car, full electric car, there is a lot of subsystems that need isolation. You have the need to manage maybe the onboard charger. The onboard charger can be unidirectional. Now it's becoming also bidirectional. So it is increasing the complexity of the system, but still you need to isolate the solution. Inside the battery management system is also required to isolate between cells. Every level of cells need to be isolated between each other. So in this case, we are more speaking about digital isolation for managing the communication from the MCU, which is managing the battery management system and their overall car. The last one is the power inverter for traction. This is a little bit more complex, and this will became more complex again because until now the car manufacturer has to provide kind of ASIL qualification from the point of view of the system. But due to the growing of the market, also the silicon manufacturer will be required to provide, for example, a driver for a traction inverter already qualified for ASIL system. If we go inside, for example, a battery charger, inside a battery charger there is just in front at the beginning the power factor correction, and now it's more and more active power correction. So you need to control, for example, a MOSFET or an IGBT or even more silicon carbide transistor. Then you have a DC-DC converter, and DC-DC converter can be, from the point of view of the primary, it's controlled with transistor, but on the secondary side you can have or passive rectification but also active rectification, because using active rectification you are able to increase the efficiency of the overall system, so you are not dissipating too much power. And on the lower side, you can see what we are able to provide you. We can provide you parts for detecting the voltages that you have inside your system, always in an isolated way. We can support isolation from 2.5 kilovolt up to 5 kilovolt, with the higher level of creepage of 8 millimeter, which is required by regulation. And we are also providing a solution for current monitoring with a differential amplifier in the front, and output which can be analog or digital at the same way. And again, devices for digital communication, for example, if you need to isolate any kind of buses for communicate information inside your system. And then all the type of gate drivers for every type of transistor technology. Inside the DC-DC converter, DC-DC converter need to be bidirectional by default, so you need to have active control on both sides of the primary and also on the secondary side. Maybe you are changing the technology that you are using from the primary to the secondary side, but still, for example, you need to isolate one side of the system from the secondary side. You can decide to isolate the primary, or you can also decide to isolate the secondary side. Is a matter of choice on the real application you have to develop. On battery management system, the most important is typically managing the communication between the devices which are balancing the cells with the batteries. And also you have to manage and control, for example, the total current that is drawing, but also the real, the voltage, which is the total voltage of the battery pack. On the driver traction control inverter, until now, driver inverter are working at lower frequencies because the motor are typically running at lower frequencies. So at the moment, the most used technology was the IGBT solution. But again, the technology is going better and better. And also in this case, silicon carbide can be the next generation of traction inverter. So in this case, we can provide isolated gate driver for, again, any kind of technology with the isolation inside the chip, and for example, for the high side driver, we are able also to provide gate driver with built-in DC-DC converter. So in order to be able to generate locally the voltages that you need to manage the high side, but also isolated each side of the three-phase system. So what we can offer to you for your project? We have a full range of digital isolator. That means every kind of system in which you need to transfer digital information. Can be unidirectional, so if you need to isolate an SPI interface, a UART interface. We have a full family of devices from 1 channel up to 6 channels integrated on the same chip, with a different level of surge capabilities. And then the family was growing, and now we are closer to release on the market a new family of devices with higher capability in terms of isolation. We will manage 6 kilovolt of isolation with plus and minus 10 kilovolt surge capabilities. A complete family of isolated analog device parts. In this case, we are managing current and voltage sensor. And then we will go a little bit more deeply on the parts. And then the family of isolated drivers. The history started with MOSFET driver, because 15 years ago was the most used solution on this application. But since the growth of the market, since the new technology that are coming to the market, we started also providing solution for IGBTs, for silicon carbide transistor, and now we are also offering solution for GaN FET solution. If you are managing an onboard charger, for example, inside the car, you have to face a problem related to the fact that you are connected to the grid. So you can capture surge lighting from the grid, and you have to protect your system against this kind of effect. So the need from the car manufacturer was to increase the surge capabilities, and for that reason we started increasing the surge capabilities to 10 kilovolt. And now with the new family that we are close to release, we are extending also the capability to 10 kilovolt bipolar surge immunity solution. Just to remind you, all our parts that are industrial or automotive qualified are qualified in the range of -40 plus 125 degrees every time. From the gate driver, so we started with the most simple solution that was for FET, MOSFET devices. And then we started increasing the capability of the CMTI, because if you need to manage silicon carbide FET or fast switching solution, you have to increase the immunity to DV/CDT over DT. So in that case, we are able to manage CMTI with a minimum value of 125 kilovolt per microsecond. We have on the family single part, so 1 channel. If you need to get the driver very close to the power transistor, but we can also offer dual parts that can be high side, low side, and in that case we are also including the overlap protection built in, and we can also managing the dead time control with a simple resistor outside the chip. So you can have hardware protection from the point of view of the dead time control. If you are going to increase again the time of switching or the frequencies, and you are looking for a solution for gallium arsenide, gallium nitride, sorry, transistor, we have released the part that are able to manage CMTI over 200 kilovolt per microsecond with in working condition. And we are immune from latch-up condition up to 400 kilovolt per microsecond. So that means that if your system has any type of glitch, any type of noise, which is below 400 kilovolt per microsecond, you are not going in any kind of latch-up condition, which is requiring to switch off the system and turn on again your system to recover from latch-up condition. In that case, again, we can offer single channel and dual channel. The dual channel low side and high side output are also isolated each other. So you can manage a power supply up to 1500 volt total. For IGBT and silicon carbide solution, we have developed a device with desaturation detection circuit built in on the chip, and a Miller clamp circuit inside the chip to ensure that the low side part of the bridge will be turned off securely. One important thing when we are managing silicon carbide transistor is to protect the part from a short circuit. If a short circuit appear on your system, you have a very short time to react and put the transistor in a safe state. And this, depending on the silicon carbide transistor provider, the typical time is 1 microsecond. This device is able to react from desaturation detection circuit detecting the short circuit condition in less than 500 nanoseconds. So you have a lot of space to keep your system safe enough and protect your system. For the isolated analog, you have two challenges normally. One is detecting the current which is flowing in your circuit, or detecting the power supply, the voltage supply. So in this case, we have a complete family of devices which use isolated voltage sensor, and those parts are single-ended input and single-ended or differential or digital output with a delta sigma modulator inside the chip. For the current sensor, the input is always differential, so you can measure positive and negative current flowing in your system. And as an output, you can have differential, single-ended, and again a digital output on the parts. The devices are very small, and we also introduced a stretched SO8 package to provide the 5 kilovolt isolation with the clearance and creepage required by regulation. And this is a kind of success story we have already on the market of the automotive. We are working with many car manufacturers. We are already qualified by them, but we are also working with many tier 1 manufacturers which are providing complete solution to the car manufacturer which are building the car. One point is if you are interested on exploring the new family of gate driver with built-in safety capabilities, please keep in touch and we can start talking directly between us. Thanks a lot.
Is there any question from the audience for the last speaker especially? Maybe one there?
Hi, I'm Filippo Savi from University of Modena. I design wide bandgap inverters and such, so I'm fairly familiar with this type of products. And I have to confess, let's say, that it was a product from your competition, let's say. But in a design, I used digital insulator for gate signals to a custom gate driver. Mm-hmm. And it was 100 kilovolts CMTI, etc. But it happened that after debugging a lot, because I never would have imagined a problem like that, it happened that on the falling edge, the digital insulator was basically turning off again, on again. So it was turning off and then returning on again for like a couple hundred nanoseconds, causing a direct short.
This is a part from us? Or?
No.
Okay.
I mean, I will not.
Okay. No. Okay.
I can disclose the.
There is an explanation on this.
Okay.
Our solution is based on capacitive insulation.
Yes.
And we were the first using simple on-off keying. So that means that in our solution there is no latch in the output. Our competitors was using transmitting along the insulation that can be inductive, can be capacitive.
Yes.
Just the let's say the pulse for set and the pulse for reset. And on the output side there is a latch for keeping the output state forever. The problem is that if there is a glitch of noise on your system, which is shorter than the pulse that you are transmitting over the insulation, the system is not recognizing the turning off of the glitch. So the latch is keeping the new level. And on our side, if there is the same type of glitch, we are just following this glitch. So if this glitch is putting your system on for a very short time, our output will be on for a very short time, but then we'll follow the input again. That could be the explanation.
Okay, thanks a lot.
Okay, maybe any other question? We are near the end of our time slot, but we can still have a couple, maybe. So let me use the last, let's say, 3 minutes for a quick question to the speakers. That could be, which in your field do you think is the biggest opportunity and the most scary threat maybe in the next years? Easy question.
Okay. I'm going to take this mask off because it's easier. Right. I think we've all been aware recently of the political events regarding gas supplies. and there's going to be a big need to transfer to renewable energy. And this is going to happen at exactly the same time as everybody's switching from fossil fuel cars to electric powered cars. And I can see as a big threat coming on energy supply security, because there's going to be so much power needed, electrical power, at the same time as we're losing the fossil fuel that will power the power stations. So that's the biggest threat. The electronics industry can help by making products which are better or more efficient. But I think generally the problem is going to be is how do we balance the fact that we're having less energy and we need more energy. So that's going to be very interesting what's going to happen in the next few years. It's a very general topic, I know, but I think everybody, including the electronics industry, is going to have to see how they can help with this, whether they can do smart grids. Maybe this problem with the legal effect of using your car as a battery will be overcome, and everybody can use their electric cars to help stabilize the grid. Maybe everybody should have photovoltaic panels on the roof. I've seen a lot more in Italy this time than the last time. In Austria, almost everybody now is having photovoltaic. I can see that will be universal. The trouble with photovoltaic is it produces electricity at lunchtime, when everybody's at work, where all their cars are at work, not plugged in, and there's no way of storing that energy at the moment. So I'm sure there's going to be a lot of investment and a lot of opportunities there for everybody involved in this business to come up with solutions and to help secure our energy supplies.
Thank you.
Thank you, Elena, for the question. So in terms of research, so this is a very exciting period. So I quote everything Steve said about so the innovation that we are facing on electrification and renewable for the grid, and also electrification of the vehicles. So with new design solution for electrical machines and the wide bandgap devices that are enabling technology for this kind of research. So there is a lot to do, and it is an exciting moment to be an engineer in this field. And also let me to mention also the other aspects, so not only the electrical and the electronics, but also all the mechanical and thermal aspects, and maybe also additive manufacturing for electrical machines. So Elena is an expert on this, and this can be a very, very important and promising solution in order to also increase performances of electrical motors. As a threat, so I agree of everything has been said. I would like to add as well the shortage of semiconductors that we are facing at this moment. And this is very important that Europe, with the European Chip Act, has launched some kind of funding for having a supply chain or increase the supply chain of semiconductor devices, which are very, very important for the future in Europe. And so there is a lot of geopolitical at the moment, and I hope not, but I think that this is one of the main threats that we can have at the moment.
Okay, on my side, I will say that we are seeing that the automotive market is growing a lot and will grow a lot in the future. But it's not only car manufacturing. We need to build a network which is providing all the energy that will be needed. Because, for example, for my job, an electric car for me is not suitable. Because, for example, if you make 500 kilometers per day, we are running out of batteries. So it's not only a problem of car manufacturing and automotive, but also providing the network outside the cars. Yes, you're sure. You're right about the shortage on the silicon provider. We were facing the same. We are facing the same problem. We have decided to provide better quantities to cars, manufacturer, and everything which is around the car, not only for the car manufacturer but also for EV charger, because if you don't provide also this kind of market, you are slowing the usage of the electric car. So it's challenging. We are working a lot on this, and hopefully beginning next year we will we'll be in a good shape.
So thank you very much. Thank you for your attention, for being here. And if you have any additional curiosity or question, please ask. If not, I wish you a good day at the exhibition. And I thank all the speakers for their contribution.
Thanks a lot. Thank you.